chance, yeah. And finally, he.
Thanks, Vinod, for the introduction, and thanks the other organizers, for asking me to give the introductory talk, opening talk for the boot camp. So this talk will be, there will be nothing really new in this talk. It's more of an introduction to the basics of lattices, and many of the things I will talk about, you will see them again in some form or another in the other talks later in this workshop. So if you've been working on lattices for a while, you'll have some nice pictures, but nothing really new there. So the plan for the talk is the following. These are the topics that I want to cover. They will not even be much about algorithms or complexity. It will be mostly about the mathematical definitions. I will start with a basic definition of lattices and certain fundamental quantities associated to lattices, which are of interest in a number of applications, and in particular also in cryptography, but the same quantities show up in other problems as well, and define the corresponding computational problems on lattices. And one interesting aspect of lattices is that for many of these problems you can consider both a worst case variant of the problem. This is the standard notion of a problem used in complexity and in algorithms. You are given an instance, an arbitrary input instance, you want to solve it. And as common in practice, you can also define random classes of lattices and consider the average case complexity of these same problems. And these two types of problems happen to be somehow connected in the lattice setting. So there is a nice connection between the two. The problems are often described with different language and different notation. And at the end of the talk, I will describe the random class of lattices. These are usually called the Q-ary lattices. All the arithmetic is performed modulo a small integer q. That makes those lattices easier to implement, their algorithms easier to implement, and those are the lattices used, for example, in cryptography. But in between, and this will be one of the main topics I will cover today, I wanted to talk about lattice duality, the dual lattice, which perhaps for the people that are new to the area is one of the most puzzling things, and sometimes it's not exactly clear how it shows up, where and why. And so I will be talking about that, and all of this will be done mostly in the geometric setting of lattices in Euclidean space, and at the end I will connect these definitions with the random lattices used in cryptography. So lattices, so the area is a long mathematics tradition. Lattices have been studied since the time of Lagrange, Gauss, Minkowski, and many other illustrious mathematicians. And they are key to many applications. Of course, even before computer science, they were useful in pure mathematics. They've been used in number theory to solve, to address many problems. For example, there is a classic simple proof that every prime number congruent to 1 modulo 4 can be written as the sum of two squares, and which is a problem that does not involve lattices directly, but you can formulate it as the problem of existence of a lattice point in a two-dimensional lattice. So at first, lattices were studied in connection to mathematics, but they turned out to be a very powerful tool to study many other problems. They are used in cryptanalysis, and Nadia, I saw her before, so we'll talk about the lattice in cryptanalysis later in this workshop, and they are used in optimization, they are used in cryptography to build cryptographic functions which are secure. So cryptanalysis was traditionally the main area of use of lattices in cryptography. They were used to break things. And one of the most interesting developments in cryptography in the last 20 years is that people found a way to use lattices not only to break cryptography, but also to build secure cryptographic functions that can be very powerful. So, so lattice cryptography, I will not talk about it, but just to illustrate a timeline. So there was, from at first with the development of the LLL algorithm, lattices were used mostly for cryptanalysis. It was in 1996 that ITI showed the connection between average case and worst case complexity of these problems, which opened up the door to applications in cryptography. But at first, the applications were very, very simple, just one-way functions, not really useful. It was more like complexity theory than cryptography, than useful cryptography. And they were also very inefficient, but there's been much progress since then. So in 2002, so this is the word that Vinod mentioned before. So I showed a first connection similar to ITI, but between lattices that have some internal structure. And I will not talk about these structured lattices today, but I'll start covering that tomorrow in the first talk tomorrow morning, and this will be covered to a greater depth later in the day tomorrow. But that's really the key. So using these lattices that are also connected to algebraic number theory is really key to get truly efficient applications from lattices. And quantum shows up in the study of lattices in many, sometimes surprising ways. So first, so you can build two types of one-way functions from lattices. I mean, they are almost the same type of the same function, but you can set the parameters in a way to make the function surjective or injective by choosing the right size of the domain and range of the function. And ITI had proved that these functions were hard to invert in the surjective setting. When the function is compressing the input, he could show that the function had a connection to worst-case lattice problems. And he was using in a very substantial way the fact that the function was surjective. And that's why one could only build a simple applications out of those functions. And in 2005, Oded Regev showed that using quantum reductions, you can prove hardness of the same type of function, but in the injective setting. And this is what opened up the door to a much broader range of applications of lattices to cryptography. So you will hear about many of these things later in this workshop. So let's get to the math. So the rest of the talk will be focused primarily on the mathematical definitions. So anytime if you have questions or if you want me to go over more details, we can always move to the whiteboard, and I'm happy to do that. I'm using the slides to, I'm not very good at drawing. Yeah, so a lattice is a set of regularly arranged points in Euclidean space. If I were to draw that on the board, it wouldn't be a lattice. So, okay, so what is a lattice? Let's start with a simple example. The simplest example of a lattice is Zn, is the set of integer vectors in n-dimensional space with integer coordinates. So it's a discrete version of a vector space. So you don't have a continuous space, you have a discrete set of points. So mathematically, you can think of this as a module over the integers. And it is a very, very simple structure. It is just n independent copies of Z. So from an algebraic point of view, it's very, very simple. Now, what makes lattices interesting is that we consider not only the algebraic structure, how lattice points can be added together to get more lattice points, but we also consider the geometry of these points in Euclidean space. And generally, you can define a lattice as the result of applying a linear transformation, an injective linear transformation, to the lattice Zn. So it is the same set of points with the same operations, the same algebraic relations, but with the points positioned differently in space. So it's still a regular set of points, but the position of the points is different. And so if you combine the structure of these points together with their positions, then you can consider notions like the length of these vectors and other geometric quantities that make sense once you think of this object, the lattice, as an object in n-dimensional space, Euclidean space. So, so this is one way to think of the lattice. So it's the set of applying a linear transformation B to the integer lattice Zn, and in some applications it is useful to think of this as starting from Zn and then you are sort of distorting the lattice. And some of the algorithms of the lattice algorithms work exactly by taking a lattice, then applying a transformation to transform it into another one, solve a problem in the other one, and then going back. But most commonly, lattices are defined as the set of all the linear integer combinations of n linearly independent vectors in Euclidean space. So all the pictures in my talk are two-dimensional lattices. Lattices are really interesting when you move to the n-dimensional case. I leave it to your imagination to think about the n-dimensional case. So in two dimension, so the linear transformation B, you can think of it, if you take the columns of this linear transformation, you can think of it as a set of vectors, as a sequence of vectors, and the point in the lattice are precisely the combinations of these basis vectors with coefficients which are integers. So it is similar to the vector space spanned by those vectors, but we only take integer combinations. So notice the same lattice can have multiple bases. So you see here we have a green set of points. Now I'm not changing the green points. The points are staying the same. I'm just changing the grid that somehow generates those points as intersections. So we have two different bases. The basis B1 here that generates all the green points, and here we have a different basis, C, that generates exactly the same set of combinations. Now, in computational applications, lattices have to be represented somehow, and providing a basis of the lattice is the most common and standard method to represent a lattice. So in algorithms, complexity, cryptography, and most applications, lattice problems are formulated in terms of a basis which is given to you as input, and then from that basis, you need to compute something. And since the same lattice has multiple bases, the problem may be easier or harder to solve depending on which basis you are given. So you can even define a lattice in a way that does not refer to a basis. You can define a lattice as a discrete subgroup, as a set of points in Euclidean space which is closed under addition and subtraction, and which is discrete. I mean, these points are far away from each other. And when studying geometrical properties of the lattice, it is often useful to forget about a basis, just think of it as a set of points with these properties. And the lattice basis comes up only when you want to solve the problems computationally. So, okay, so quantities. A fundamental quantity associated to a lattice which shows up in pretty much every application is the lattice determinant. Now, so given a basis of a lattice, B, you can define a fundamental region of the lattice as the parallelepiped that is spanned by the two basis vectors. And you can compute the volume of this parallelepiped. And so this quantity is called the determinant of the lattice. And since the lattice has multiple bases, you may choose different so for some reason it's showing differently. So, okay, so those parallelepipeds are shaded on the computer, but they don't. Okay, so you can consider different bases. So you can have different fundamental regions, but all these fundamental regions have the same volume. So the determinant is not a property of the basis, but is a property of the lattice itself. And not only that, it can also be computed efficiently from any basis. Just a matter of recalling a few geometric formulas, how to compute the volume of a parallelepiped, and we'll see soon a simple way to do that. Now, another way to think of this determinant is in terms of lattice point density. You can define, for this it is, so this is best illustrated by considering a fundamental region where the basis vectors are taken with coefficients between plus or minus 1/2, so that these fundamental regions are centered around the lattice points. Now, these parallelepiped, they span the entire space. In fact, they form a partition of the space. If you take a large enough ball in Euclidean space, you can see that the number of parallelepipeds, except for those that are only partially included in this sphere, so the number of parallelepipeds is proportional to the volume of the sphere. And as this sphere gets larger and larger, this ball gets larger and larger, you can expect this. You can expect the number of lattice points inside the ball to approach in the limit exactly the volume of the sphere divided by the determinant of the lattice, divided by the volume of each of these individual bricks. And so from this definition in terms of density, it is immediate to see that the determinant does not depend, or shouldn't really depend much from depend on the basis, because it's just defined in terms of number of lattice points inside a large, sufficiently regular region of space. Okay, so there are other quantities associated to a lattice. Determinant is a quantity that can be easily computed. Given a basis, it is easy to figure out what the determinant is, and you can think of it like a sort of scaling factor. So since you can compute it easily, in many lattice problems, you can assume the determinant of the lattice is 1. If it's not, you can scale it, and you can think of the determinant as a normalization factor that is useful to normalize the density of the lattice point in space. Now, two lattices, even if they have the same density, can still have quite different geometric structure. So on average, they may have the same number of points per unit volume, but the position of these points, the points can be arranged in very different ways in n-dimensional space. So there are other quantities associated to a lattice for which no efficient algorithm is known. And some of the most fundamental quantities are the successive minima of a lattice, starting from the minimum distance. Now, given a lattice in 2 dimensions, you can consider the distance between any 2 points in the lattice. And since you can always add up and subtract lattice points, you can always assume that one of these 2 points is the origin. Just subtract one of the 2 points from both of them. So and you can consider the 2 points which are closest to each other. And so this is the same as the distance of the lattice point, is the length of the lattice point closest to the origin. And this is called the minimum distance of the lattice, or also the first minimum of the lattice. It is the length of the shortest non-zero vector in the lattice. So this quantity is easy to compute in 2 dimensions. Gauss already, or Lagrange before him, figured out even efficient polynomial time. There was no notion of computing or polynomial time at the time, except for computing by hand. And so what is used today to compute the length of the shortest vector in a 2-dimensional lattice efficiently is essentially an algorithm due to Lagrange a while back. And so we don't know how, in 2 dimensions it is easy to compute, but in n dimensions the problem is much harder. And especially given a basis, because this minimum is just a point in the lattice, it's not necessarily one of the basis vectors. So I can give you a basis with long vectors, and we'll see that soon how that can happen. But before we do that, let me introduce a few other parameters that come up in different applications. We can generalize this lambda 1, the first minimum, the length of the shortest vector, to a sequence of values, lambda 1, lambda 2, all the way to lambda n, where n is the dimension of the lattice, where lambda I is defined as the radius of the smallest ball that contains at least I linearly independent lattice vectors. Now, notice how as soon as you put a ball around the origin that contains a non-zero lattice point, you will have not just one lattice point, you will have more than that. You will have at very least the origin, the lattice point, and its opposite. So you will have 3 lattice points. But these points are on a line. So they span a one-dimensional space. If you take a bigger ball, then you may find a vector which is not in the line spanned by the first vector. So you will get a linearly independent lattice point which is slightly longer, and the volume, the radius of this larger ball is called lambda 2, the second successive minimum of the lattice. Well, in 2 dimension, that's where it stops. In n dimension, you can go beyond 2. You can go all the way up to lambda n. And as an example, if you take Zn, the lattice of all the integer points, so without applying a linear transformation, so it's easy to see that this lattice has n linearly independent vectors of length 1, the standard basis of the integer lattice. So in that case, the first n minima are all the same, and they are all equal to 1. But that's not true in general. If you apply a linear transformation to this lattice, you will end up with a typically increasing sequence from lambda 1 to lambda n, and that's very easy to construct. So you can try to, for the students in the audience, you can try to come up with an example as an exercise of a lattice where lambda 1 to lambda n are any values that you want. So you can choose those values and then build a corresponding lattice that achieves those values. Okay, so other quantities so there are many other quantities associated to a lattice. One is a distance function. So if you are given not only a lattice, but also a target point, t, the blue point here in the picture that does not belong to the lattice, you can consider the distance between this point and the lattice. So if t happens to be a lattice point, then this distance would be 0. And if you go far away from the lattice, this distance will increase. And for every point, you can consider the distance to the closest lattice vector. And you can also consider the maximum of this function. The minimum is 0 if you set t as a point in the lattice. But you can move the target around in space until the distance is as large as possible. And it's not hard to see that when you achieve this distance, if you put a ball around a target, you will have n different points on this sphere that somehow trap your sphere. You cannot move. So here this point T, if you move it to the right, you can increase the radius of the sphere without touching other lattice points. So as long as there are less than n points on the surface of this sphere, you can increase the distance. But at some point, you will get into a local maximum where you can. So if you move the sphere in any direction, you will either include one of the lattice points inside the sphere, or you will have to shrink the radius of the sphere and get closer to the lattice. So in general, so this is called a hole in the lattice, and it typically corresponds just to a local maximum of the distance function. But you can also consider the global maximum. So if you consider the largest possible value of this function in space, that's called the covering radius of the lattice. And you can think of it as the largest distance that you can be from the lattice while staying in the same linear space. Of course, if you move orthogonally to if this lattice is spanning a lower dimensional lattice and you move orthogonally to that plane, you can get as far as you want. But let's say that you are not allowed to do that. In fact, for this talk, for simplicity, I will assume that all the lattices are full dimensional. They span the full n-dimensional space, and that will make a number of definitions simpler. So the covering radius is this maximum distance, is the maximum of this function. And another way to look at it is by putting spheres around every lattice point. And so these spheres at first will be disjoint. And you can increase the radius of these spheres. At some point, these spheres will start intersecting with each other. And they start intersecting exactly when the radius of the sphere becomes more than half the minimum distance of the lattice. So if there are 2 points at distance lambda 1 from each other, if you set the radius of the sphere to lambda 1 over 2, then the spheres will touch in one point. But you go beyond that. You keep increasing the radius of the spheres until they cover the entire space. And once they cover the entire space, the radius of these spheres will be exactly the covering radius of the lattice. So that's why it's called covering radius, because it is the radius that is required to cover the entire space with spheres that are centered around lattice points. Okay, so these are the most important classic quantities associated to a lattice. So there is one more quantity, and this is something that came up only recently, something that Oded Regev and I introduced in 2004 based on some previous work of Oded. Oded started working on these problems from the quantum side, and then some of the techniques and results started percolating to the classical side. But in 2004 we defined a quantity called the smoothing parameter of a lattice that ended up playing and still plays a fundamental role in the study of the average case complexity of lattice problems, and that's something I will talk about tomorrow, but let me just define the quantity. We do the same as we did before. We put spheres around the lattice points and we make them bigger and bigger. At some point these spheres will cover the entire space. That's the covering radius of the lattice. But notice, even if we cover the entire space, some regions of space are darker, some of them are lighter. So that means that we are covering the space, but not in a uniform way. So we increase the radius of these spheres. We make them larger, and we can make them even larger than that. And notice, as these spheres get larger and larger, the color of the picture will get closer and closer to uniform. In the limit, if you set the radius of these spheres to infinity, then every point will get exactly the same color. Now, you will not get exact uniformity for any finite radius, but you will get closer and closer to it. And once you're happy enough, you say, okay, so now it looks all the same color to me. You can stop. And it turns out that you don't need to make these spheres that long. So these spheres should have a radius at least equal to the covering radius of the lattice, which in general can be as large as square root of n lambda n. So square root of n lambda n would be tight in the case of Zn, the integer lattice. So if you make your sphere larger by a logarithmic factor, then you will be very close to uniform. So this is best done using not uniform distributions over spheres, which have a sharp boundary. So this is best defined using Gaussian distributions, because the way these bounds are proved is using harmonic analysis, and this is most easily done using Gaussians. So this is usually formulated using, instead of spheres, Gaussian noise added around every point. And you take Gaussian noise with width that is slightly bigger than lambda n. So every component of the radius has expectation equal roughly to lambda n, a little bit more than that. And that's called the smoothing parameter. It is parameterized by some error term epsilon, which represents how close you want to be to uniform. And it's a quantity that you will hear more about, mostly I think tomorrow, or perhaps also later today in some of the algorithms.
So Daniele, can you replace the square root n lambda n by the covering radius? Is that, in the sense, if you take Gaussian?
Yes, but it's a worse bound, because this quantity is so the covering radius is always, it is at most square root of n lambda n. Oh yeah, it is at most square root of n lambda n. And, you say, can I lower it to that?
Smaller Gaussian.
Intuitively, yes, but I'm not sure. I think we tried to prove, at least back then we couldn't prove it. I remember, trying to prove, to show the bound. So that's, you're going to talk about it? Yeah?
I'm not going to talk about it, but yeah, we can replace it with the.
You can replace it with the, So.
Who's we?
Myself and Oded.
Okay.
Okay.
So yeah, so there's been much work, so using Gaussian techniques, and there's been work on, I mean, this smoothing parameter that we defined just for technical reasons, and we gave a name to it, which after, in retrospect, is not that good of a name. I mean, smoothing is fine, just the word parameter is not exactly a good one, because it clashes with too many other things. Yeah, so these days it is considered interesting lattice problem on its own. Given a lattice, estimate the value of the smoothing parameter. The same way as you can try to compute the minimum distance or the covariant radius, computing the smoothing parameter is a problem with its own study of complexity and algorithms. This is a good part work by Noah that will be talking about something else later today, but he's the expert. Okay, so I will not be talking about that. It was just to introduce the quantity. You will see this at least tomorrow. Okay, so what can we do about these quantities? So determinant can be easily computed. Now, what about lambda 1? I told you we don't know how to compute it. But it's still possible to bound these values. It is possible to compute upper bounds, in some cases also lower bounds to these values. And this is a fundamental theorem of Minkowski that it's called the convex body theorem because it is, in its simplest form, it is formulated just using Zn, the simplest lattice, and an arbitrary convex symmetric convex body. And the theorem says that if you have a body, C, some region of space, which is symmetric, convex, and it has a volume which is at least equal to, or for simplicity, let's say strictly greater than 2 to the n, then C must contain an integer point. And I will not, the proof is not hard, but I will not show you the proof, but let me give you just an illustrative example. So we have the set Zn of green points here in the picture, and I ask you, can you take out a region of space that does not contain any green point other than the origin? And so the best way to do it, I mean, showing that there is no better way to do it, that's a little bit, it's an exercise. It's a little bit harder, but if you work on it, you will easily come up with the following candidate solution. You can take a cube, hypercube in n-dimensional space, centered around the origin, and offside that is just slightly less than 2. Or perhaps you can make this an open convex body without a boundary. So if you do this, you will get a body which has volume 2 to the n. So this distance is 1, the distance between two green points. So the side of the cube is 2. The volume of the cube is 2 to the power n. And it does not contain any lattice point beside the origin. But the moment that you reach volume 2 to the n, or you make it bigger, then you will have a lattice point in it. And I challenge you to find a bigger area, bigger than 2 to the n, that does not touch any green lattice point. If you try to solve it by drawing pictures on a piece of paper, you can probably entertain yourself for a short while, but after a while you will give up and then try to prove that there is no way to do it. And so Minkowski's proof is just a little bit more than an application of the pigeonhole principle. So it is a nice geometric, ingenious proof, but it's an elementary proof. It does not involve any heavy tools from mathematics. Now, what does this tell us about arbitrary lattices? This doesn't seem very interesting, it's just Zn. Well, we know that every lattice can be obtained by applying a linear transformation B to Zn. And linear transformations preserve symmetry and convexity. So if you have a symmetric convex body, and then you apply a linear transformation, then you will get a different but still symmetric and convex body. The volume of the body will change, but it will change exactly by the determinant of the linear transformation. So using this, you can apply your linear transformation to transform any lattice back to Zn. So if you start from a lattice, let's say that the lattice is defined by basis B, or linear transformation B. You can compute the determinant of the lattice, and let's take the nth root of the determinant so that it scales linearly with a lattice. Let's call it R, and let's take a cube of side R. And no, let's take a, yeah, so let's take a cube of side 2R. And then let's apply the inverse linear transformation, B inverse, to this cube. We get, so here the transformation is just a rotation, more general, just because yeah, that was the easier one to draw on the slide. But generally, so this is an arbitrary linear transformation. So this one, the rotation doesn't change the volume. So in general, the transformation will change the volume. But so this transformed cube is a convex body of volume which is equal the determinant of B inverse times the volume of the original cube, which is 2R to the power n. So here you have this term, 2 to the n, and then the determinant, the inverse determinant of B and R to the power n cancel out, because we chose R to be exactly the cancelling factor. So you get a convex body of volume exactly 2 to the power n, which must contain an integer point. And once you have an integer point that is non-zero, you can apply the linear transformation B back to it and obtain not an integer point, but a lattice point in the original convex body. And so this typically applied from very simple convex bodies, like Euclidean balls. And that can be used to bound the length of the shortest vector in a lattice in the Euclidean norm. But it extends also to bounding the length of the shortest vector with respect to other norms. If you want the L infinity norm, you would consider a cube. If you want the L1 norm, you would consider the corresponding ball. And in general, for any norm, there is a corresponding symmetric convex body that defines the unit ball with respect to that norm, and it gives a powerful technique to bound those quantities. In the Euclidean case, so this shows that the shortest vector in a lattice, or the first minimum, lambda 1, is always at most square root of n times r, and where r is the root determinant of the lattice that you can think of as a normalization factor. Now this square root of n comes from the volume of the n-dimensional ball in Euclidean space, and you can get a slightly better constant factor before the square root of n if you put the exact volume. And it can also be further improved a little bit beyond that, but asymptotically that's the best that you can get. There are lattices where the shortest vector is as large as square root of n, order of square root of n, the root determinant. Now, this theorem of Minkowski sometimes is called the first theorem of Minkowski. There's a second theorem. I'm sure he proved more than 2 theorems. But so these are the standard names, and probably these were not the very first 2 theorems that he proved. But so the second theorem is a strengthening of the first one that says that this quantity, square root of n times the root determinant of the lattice, is not only an upper bound on lambda 1, but it is an upper bound on the geometric mean of all the successive minima. So you can take not only lambda 1, you take the product of all the minima, and then you take the nth root of their product. So this is bigger than lambda 1. It's going to be between lambda 1 and lambda n, somewhere in between. And you can still prove the same upper bound. And interestingly, this is proved by applying linear transformation to your lattice, though the linear transformation is a little bit more involved. In this case, it involves orthogonalization, which I'm going to describe next. Now, so lambda 1 in general can be arbitrarily smaller than Minkowski's bound. So you can have lattices that have a very large determinant and very small minimum distance. Just add one more component orthogonal to your lattice and make it bigger and bigger. It will not change the shortest vector, but it will increase the determinant of the lattice. But if you take this quantity, since it involves all the successive minima, it somehow captures the whole n-dimensional structure of the lattice. And we know that the square root of, so this is an upper bound on the quantity, and this quantity is never smaller than Minkowski's bound, more than square root of n. So it is a closer, sharper quantity associated to this value. Now, so this value is tight, meaning that there are lattices where the length of the shortest vector, or even this product, is at least as big as the square root of n, the root determinant, multiplied by not too small constant. And constructions of these lattices are not particularly simple, they involve quite a bit of mathematics, but it is much easier to prove that this is true using probabilistic arguments. If you pick a random lattice, according to the distribution that we'll use later today, it's a sort of standard exercise to prove that random lattices achieve Minkowski's bound within a small constant. I think the constant is something like 2 or 4, so it's a fairly tight bound. Okay, so so these are quantities associated to a lattice, geometric properties of the lattice. Each of them defines a corresponding computational problem. So for the first minimum, lambda 1, the problem is called the shortest vector problem. So you are given a lattice typically represented by a basis, and the question is, can you find, so you are given these 2 points, b1 and b2, which in general can be very long. Now notice, even if these vectors are fairly long, if you take the set of all their linear integer combinations, you will end up many smaller vectors, because b1 and b2 can somehow cancel with each other. So given b1 and b2, can you build the lattice, which you cannot build it explicitly and enumerate all the points, it's an infinite object, but can you in principle consider all the lattice points and find among all these lattice points the smallest one? So if you put a sphere around the origin, you can make the sphere larger and larger until it touches the lattice point, and that's the solution to the problem, which in this specific example is obtained by taking 5 times b1 and then subtracting twice b2. And so these coefficients that are required to combine the basis vectors can be arbitrarily large depending on which basis you are given, and there is no known algorithm to solve this problem. In fact, efficient algorithm. In fact, there is no known efficient algorithm even to solve this problem approximately in the following sense. So let's say that we relax the problem. Instead of asking to find the shortest vector, a vector of length lambda 1, we ask to find a vector that is not much longer than that. Let's say longer than lambda 1 by at most an approximation factor gamma. So you can make this sphere bigger, say by a factor gamma, so in this case it is twice as big, and I ask you to find a non-zero point inside this larger ball. It's not going to be the shortest, but it's going to be short. It's going to be an approximately shortest vector. Notice it's not an approximate lattice vector. It has to be a lattice vector. It has to be exactly in the lattice. But the length is not far from the optimal. And so this is the approximate shortest vector problem, and for sufficiently small approximation factors, there is no known polynomial time algorithm. So now I will talk more about what sufficiently small means. Before then, you can try to make your best guess. How small should this gamma be before, for the problem to be hard to solve? And okay, so another problem that is associated to the distance function is the closest vector problem. So you are given a lattice and also a target point t. Again, if I just give you this input, it's not clear what the answer should be. Which combinations of these 2 points, how close can you get to t by taking an integer combination of b1 and b2? Is not entirely clear from the basis. If you take all the lattice points generated by b1 and b2, you will see that one of them is fairly close to the target. You put a sphere around the target, and there is a fairly small sphere containing a lattice point, and that lattice point is the solution to the closest vector problem. And again, you can consider an approximate version of the problem. Instead of finding the closest vector, the point at distance mu, where mu is the actual distance of the target from the lattice, let's relax it to gamma mu, or 2 mu for concreteness, and this is the approximate closest vector problem. So for each of these problems, you can also define a just distance estimation version, where you are asked to approximate the value of mu without necessarily finding the point achieving the distance. I will not make much of a distinction between these two problems in my talk, but the distinction between the two problems comes up typically in complexity theory. The distance estimation version of the problem is the one that is most commonly studied. And of course it is an easier problem, just estimating the distance or the length, but it already captures the hardness of many of these problems.
So then, is it typically the case that the hardness is proved for the approximation version, and algorithms are for the easier approximation version, and the algorithms are for the harder finding the closest vector?
Yes, mostly. Yeah. So the vast majority, let's say all but one, algorithms that solve this problem. Yeah, there is one. Of these algorithms, so if you wanted to solve the problem algorithmically, typically we don't know how to solve the length estimation problem any better than by finding the solution. So algorithms usually solve the search version of the problem, and hardness typically, if you can prove that the problem is hard in the search version, that's because you can already prove that the problem is hard in the distance estimation version. So based on, say, experience, it seems that the two problems are equivalent, but we don't really know how to prove the equivalence. For the exact version of the problems, there is a simple way to reduce, to show that the problems are equivalent, but in the approximate setting is not the case. So there are a few exceptions in the algorithm literature where you can estimate the distance without, it depends on the approximation factor. If you just ask it to approximate the distance rather than finding the solution, you can achieve somehow better approximation. Okay, so one last problem, and this problem is perhaps less common, but it became really a central problem when with lattice cryptography, because it's probably the most relevant problem for lattice cryptography, is the one associated to lambda n, the last successive minimum. This is called the shortest independent vectors problem. And you are asked to find not just one short lattice vector of length at most lambda 1, you are asked to find n linearly independent lattice vectors of length at most lambda n. Notice they can all be bigger than lambda 1. You can define a harder version of the problem where you want to find a vector of n linearly independent vectors of length achieving exactly lambda 1, lambda 2, all the way up to lambda n. But in the most common formulation, you just consider the lambda n upper bound, and you want to find those points. Again, so this is our usual lattice. You are given just a basis as input, and you put a sphere around your the origin, and you make this sphere big enough of radius. You set the radius to lambda n so that it contains n linearly independent vectors, and you want to find them, or perhaps you just want to estimate the value of lambda n. And as usual, you can consider the approximate version of the problem. Okay, so far so good. These are the basic definitions of lattices and the quantities associated to them, and okay, I think there is something wrong with where this slide shows up. So let's just move on. So let me just illustrate where this problem comes up in one very simple application, for example, outside of cryptography. So in coding theory, lattices are used in the design of error-correcting codes for, say, multi-antenna systems. So you have many antennas transmitting a signal, and you have also receiving antennas on the other side, or perhaps just one receiving antenna where you receive all these different signals. Since the antennas have different positions or geometric properties, you will get slightly different versions of the transmitted signal, or you can even send different, you can try to code your message by sending different messages on each of these antennas. And these transmissions will be subject to noise, which is typically modeled as white Gaussian noise in transmission channels. And if you think of these antennas as coordinates of an n-dimensional space, you are transmitting a vector and you are receiving a perturbed copy of the vector, this vector with some error added to it. And recovering from the error and recovering the original message that was sent is precisely the problem of finding the closest lattice point. So the encoder sends the message as a lattice point, transmits it over a channel, then this message is received but subject to some error. So you get a point t which is closed to the vector that was sent, and recovering the lattice point closest to it gives a way to obtain the original message m. And so in this setting, you can see that the closest vector problem corresponds to decoding. So that's the decoding problem, recovering the original message from the noisy received message. The shortest vector problem, which is computing the minimum distance between any two lattice points, is the problem of evaluating or estimating the error correction capability of the code. Now, if the error is bigger, if the noise is bigger than the distance between two lattice points in your lattice code, then different messages may get confused with each other. So you want to design lattices that have large minimum distance so that different messages, different lattice points are not confused. And so SVP is evaluating that, and SIVP also corresponds to a standard problem in this type of applications, which is related to distortion in vector quantization. If you are trying to map arbitrary point in space into something discrete, perhaps for storage purposes or some other application, then the covering radius of the lattice or the lambda n parameter of the lattice corresponds to how much you need to change your input point to represent it as a lattice point. Okay, so there are some special versions of the closest vector problem which are closely related to these applications, and they also happen to be closely related to the way lattices are used in cryptography. So these are both versions of the closest vector problem. Let's consider a version where you are given a lattice, a target vector t, and also a distance d. And the question is, find a lattice point within distance d. So I give you the target distance. And notice, if you don't know the distance and d is arbitrary, you can always try to do binary search on d to find the closest lattice point. So being given this distance as an additional parameter doesn't make much of a difference in general, but you can consider restricted versions of the problem. One of them, called the bounded distance decoding problem, is a restriction of CVP where the distance of the target to the lattice is guaranteed to be within the unique decoding radius of the lattice. It is less than lambda 1 over 2. So in this setting, you know that you can decode your message and the solution is unique. There is at most one point within distance d from the target, and this is an easier problem than CVP because you are promised that such a point exists. So it is CVP when the target is fairly close to the lattice, which intuitively makes the problem easier. It is easier to find the closest lattice point if the lattice point is close, if I already give you a good hint, a point that is close to it. So another version of the problem, which goes under several different names, sometimes it's called the guaranteed distance decoding or absolute distance decoding. So here the distance d is set to be at least the covering radius of the lattice, so that the solution is not unique, so there may be more points within distance mu from the target, but this time the solution is guaranteed to exist. No matter which target point you are given, you know that there is always a point within distance mu from it. And you are asked to find such a point, which is not necessarily the closest one to the target, but it is still within this worst case bound. And so this corresponds to functions that are built from lattices, which are either injective in the first case or surjective in the second case. So how these problems relate to each other? There's a whole bunch of relations that can be proved, connecting them one with the other. No, I will talk about other results in complexity of lattice problems. But let me just give a brief summary. So you can group, so We don't know how to show that all these problems are equivalent to each other, but they are roughly grouped in 3 categories. So there are CVP and CVP. These are the problems that we all like and love, and we don't know how to do anything from them. Then there are the problem SIVP and ADD, which are equivalent to each other, and they can be used to build one-way functions, simple cryptographic applications, private key crypto. So this is what was used by Aitai in his first result. And then you can consider this other class of problems where you're only asked to find the length of lambda 1 or lambda n, or approximate it. That's why it's called gap, or the bounded distance decoding. Again, these problems can be shown to be somehow equivalent to each other, and there are reductions going down, and these are the most powerful problems that allow to build all the lattice cryptography that was developed in the last 10, 15 years. And I will not show how the reductions work except for one, and I'm doing this for illustrative purposes to introduce the dual lattice. I mean, some of these reductions, here we will not use it. But let's consider first a simple example. So the absolute distance decoding reduces to SIVP. If you can compute n linearly independent vectors in a lattice, then you can always sort of approximate this special version of the closest vector problem. So you are given a lattice L and a target T. So what can you do to find a point in the lattice which is not far away from T? You can first solve the shortest independent vector problem in the lattice to find n linearly independent short vectors. So this will tile the entire space into regions, and then you can round your point T with respect to these regions. Once you have a good basis, you can just compute the coordinates of T with respect to the V1, V2 basis, and round the coordinates of T with respect to it. And this will always give a point in the lattice which is within a distance equal to the, at most, the diameter of the fundamental region. And if this fundamental region is defined by vectors of length at most lambda n, then the diameter will be at most n times that. If these vectors are orthogonal, it would be square root of n. But in general, if these vectors are close to parallel, then it can be n times bigger. So it's not an exact reduction. You lose a factor n when going from one problem to the other one, but you can show a connection between the two. Now you can ask, can I prove a similar reduction for the bounded distance decoding problem? And the answer is yes, but in order to do that, you need to use the dual lattice, which is what I'll be talking about next. So let me just skip this. This is just a simple example where the lattice is not orthogonal and the rounding doesn't produce quite the right solution. But let me move on and talk about what techniques are used, some of the most basic techniques used when studying lattice problems. One is called size reduction. So you are given two basis vectors, B1 and B2, and then a target point T in space. And the question is, can you make T shorter using B1 and B2? And it's easy to see that by subtracting copies of B1, you can always bring T within a sandwich region of space of width equal to the length of B1 centered around the origin. And you can do the same also for B2. And you know, as you do it for B2, the point in general may go outside the first region. But every time you do this size reduction procedure, the length of your vector is always getting shorter. So you will not get into loops. The point will get shorter and shorter, and at some point you will be in the intersection of all these sandwiches. So you will be inside this parallelepiped defined by the basis vectors. Notice that this parallelepiped is not the one spanned by B1 and B2. So the sides of this parallelepiped are orthogonal to B1 and B2, and we'll see why this orthogonality comes up in this setting as we define the dual lattice. But So this size reduction can also be used to define certain approximation algorithms for lattices. And many of these algorithms, or also geometric properties of the lattices, are proved using projections, orthogonal projections. So Zn is much easier to analyze, and ideally we would like to transform every lattice into some copy of Zn. So this can be done using the standard Gram-Schmidt orthogonalization process, where given a sequence of vectors b1 to bn, you can define bi star, the component of bi, orthogonal to the previous vectors by... So b1 is the same as the b1 star, but for b, so what we do for b2 is to shift b2 in the direction of b1. You consider the entire line, or more generally hyperplane, centered on bi and spanned by the previous vectors, and you make b2 as short as possible by subtracting copies of the previous vectors. And notice here we are allowed, in Gram-Schmidt, you are allowed to subtract copies with non-integer coefficients. So when you orthogonalize b2 orthogonally to b1, you will get with a point which does not belong to the lattice. So this is an operation common in linear algebra, may not seem an operation that plays well with lattices, but it's still very, very useful. And the reason it is useful is because, so what you get is an orthogonal basis of the Euclidean space spanned by the lattice. This is not a basis for the lattice, because there are certain points, you have points which do not belong to the lattice, and you're missing other points. But still it is useful. For example, by computing these orthogonalized vectors, you can evaluate the determinant of the lattice. You can also see from this form, which is equal to the product of the length of the orthogonalized vectors. You can also get a simple bound on the determinant of the lattice just as the product of the basis vectors. And finally, you can use this as a lattice rounding procedure. I will not go over the details of the algorithm, but the intuition is that instead of considering the parallelepiped defined by the lattice, you can consider the parallelepiped defined by the orthogonalized basis. And even if it's not a basis, it still forms a partition of the space. And you can still round a target point to the corresponding region. So even if these regions are not defined by lattice vectors, they can still be connected to the lattice point using some form of rounding procedure. And this something can be done efficiently by considering these vectors one at a time. And it gives a way to take any point in space and always finding a point in the lattice within a distance which is equal to half the diameter of this orthogonalized parallelepiped. And since it is orthogonal, you get somehow better approximation. You get better quality answers than rounding with respect to the basis. So this is an upper bound on the distance that you get when performing a rounding. But notice, if I give you a target point within a smaller distance to the lattice, more precisely within a distance which is at most half the internal radius of this region, then you will find, you will be guaranteed to find the closest lattice point. So we have, so this region defines two spheres, the one inside it, the one outside it, and if you are inside it, then rounding will find the exact solution to CVP. If you are outside it, you will find something which is not much bigger than that. But in the second case, you know that you were not that close to the lattice to start with, so you still get an approximate solution. So combining these two elements, you get that you can approximate lattice points, you can approximate the closest vector problem within a factor that is proportional to the ratio between the largest and the smallest orthogonalized vector in the orthogonalized basis, times the square root of n factor that comes from Pythagoras. And of course, this requires to find a good basis, a basis where these BI stars have lengths which are close to each other, which is not always possible. but it says that if you can find a good basis for the lattice, then you can use that to approximate the closest vector problem. Okay, so dual lattice. So from an algebraic point of view, the dual lattice can be defined in a number of different ways. One way that I like to think of it is the following. So by analogy with vector spaces. Now a vector space over the real numbers is a set of vectors that is closed under addition and multiplication by scalars. You can multiply vectors by any real numbers when you have a vector space over the reals. And the dual of a vector space, usually denoted as V subscript V, it can be defined abstractly as the set of linear functions from the vector space to the real numbers. And now linear functions can be easily represented as scalar products. So any linear function from V to R can be represented as a function that takes a vector y as input, and it takes the dot product between y and some vector x, which defines the linear function. And so it is a linear function from V to the real numbers. Now the dual of a lattice can be defined similarly as the set of linear functions from the lattice, which is a subset of the vector space, the set of lattice points, to the integers. So we want only linear functions that produce an integer value as a result, rather than arbitrary linear functions. And again, these functions can be represented as vectors in the linear span of the lattice, though they will not necessarily be lattice points. They will be linear functions which happen to take integer values when you evaluate them on lattice points. So if you take this representation, then the dual of a lattice is defined as the set of all vectors in the linear span of the lattice, such that the scalar product between this dual vector and any lattice, any point in the lattice, is an integer value. Okay, so let's see some examples. Okay, so let's consider this lattice, Zn. What is the dual of Zn? What are the vectors that always have integer scalar product with Zn? I guess? Yeah? It's Zn, so it's the same. So if you take integer vectors, they have integer scalar product, and I'm putting the points a little bit to the side just so that you can see both of them, but they are exactly the same point. If you take a point that has non-integer coordinates, then one of the scalar product will be non-integer, so it's not in the dual. Okay, so far so good. So that's easy. So we can compute the dual of Zn. Now, let's apply a linear transformation. Let's rotate the lattice. What is the dual of a rotated lattice? Now, scalar products don't change under rotation. If you take two vectors, you rotate both of them by the same amount and compute the scalar product, you obtain the same value. So also the dual lattice gets rotated. So you get again Zn. So let's see if you can find a lattice where where you get something different. What if you scale your lattice? You take your lattice and you multiply it by a factor q. What would be the dual? What do you expect to happen to the dual? You want the product to... Good, yes, that's the answer. So, so since you want the product to be the same, if you are if q is bigger than 1, if you are scaling up the lattice, the dual lattice will shrink. Okay? So this already suggests that dual lattice, in many ways, it behaves as a sort of inverse of the lattice. Now, lattice is not a number, so it's not just the inverse of a number, but it has a sort of inverse property. Okay, so let's get something more interesting. Let's consider an arbitrary lattice. What is the dual of this one? Good. So I see that, you all have the answer. This is the answer. It's a mess, okay? Okay, so it really looks like a mess. I didn't add any lines. We have just the original lattice and the dual. And let's remove the lines to see what's going on here. Now, if you remove the lines, it may even look like that I was a bit sloppy when drawing it. So some of those points don't look like quite in the right position. Yeah, it looks like that I used the PowerPoint to draw the slide rather than writing a program that places the lattice points where they should be. But indeed, no, they are in the right place. They are exactly a lattice. And so you can see that, there are certain basic properties of the dual lattice which can be understood in terms of being sort of inverse of the other. Like, for example, if you take a if the lattices are in the same, if they are full rank, if you add more points to the lattice, you will lose points in the dual lattice because you have more constraints to satisfy. The dual of the dual is itself, but you can also take scalar products between lattice points, between a point in the lattice and a point in the dual. That's used in the very definition of dual. However, something that doesn't make any sense is to add up a point in the lattice and a point in the dual. So that's a meaningless operation. So in some sense, these two lattices, they do not live in the same vector space. They are in isomorphic vector spaces, but the best way to think of them is as, say, points and functions. So you can apply the function to the point, but you cannot, there are different types of objects, even if they can both be represented as vectors. Now, the fact that you can take scalar products, that's a key property. That's what is used. Whenever you use the dual lattice, you're using this property. And you know that, so the black points are the original lattice. So here the red points are the dual. So let's take one specific lattice point in the dual. So this red dot here, okay? It's not in the lattice, it's some point in space. But we know that when you take the scalar products between the dual point and the black points, you always get an integer. So depending on which integer you get, you can partition the lattice points into layers. All the points that have scalar product 0, all the points that have scalar product 1, all the points that have scalar product 2, and the same also for the negative numbers. So the dual lattice points represents way to partition lattices into layers. And the distance between layers in this partition is exactly equal to the inverse of the length of the dual vector. If you take a longer dual vector, you will get a different partition of your lattice, of the black lattice into layers, but the layers will be closer to each other. So each dual lattice point is a partition of the lattice into layers. And many algorithms, they use dual lattice points exactly to perform these partitions and then perform some type of enumeration or bounding. So one simple property that is easy to see is that we know that the distance between the layers is the inverse of the length of the dual lattice point. You can always put a sphere in between layers. And since it is in between layers, it does not contain any lattice point because the lattice points are in the layers. So this provides a lower bound on the covering radius of the lattice. So if you can find a short vector in the dual lattice, the short vector will give a partition where the layers are far apart from each other, and you will have these big gaps between layers where you can put a sphere without lattice points in it. So if you have short points in the dual lattice, then necessarily you must have a large covering radius in the primal lattice. If lambda 1 of the dual is small, then mu of lambda of L is large. So this is an example of a transference theorem that the strongest transference theorems were proved by Banachik in the early 90s. So there were previous bounds proved by other mathematicians, including Hermit and Minkowski, where this number was much bigger than n. It was originally an exponential term. So you can relate, so lambda 1 of the lattice and the covering radius of the dual, they are related by an approximate inverse relation. The product of these two numbers is always between 1 and n, where n is the dimension of the lattice. And something similar can also be proved for the successive minima if you take two successive minima at complementary indices, the lambda I of the lattice and the lambda n minus I plus 1 of the dual lattice. Again, this product will be always between 1 and n. So, so this is useful, for example, to prove co-MP results. If you want, so how can you show that a lattice does not have short vectors? I mean, showing that it has short vectors is easy. You can prove it by exhibiting such a short vector. So if you want to prove that such a short vector does not exist, well, you can show that a dual lattice has n linearly independent short vectors. And by the transference theorem, they will give a lower bound on lambda 1 in the original lattice. So these proofs, they involve harmonic analysis and other mathematical techniques that are a bit beyond the scope of this talk. So let me cover something that is much simpler, which is how to relate the bounded distance decoding to the shortest independent vector problem. Remember, we did something similar before for the absolute distance decoding. We said that, if you take a basis, if you find a good basis corresponding, say, to n linearly independent vectors, now, these n linearly independent vectors are not necessarily a basis, but if they are not and they are still shortest, they are still good for rounding. So if you do that, you can, if you do rounding with respect to the shortest basis, then you get a good solution within some worst case bound related to lambda n, to the quality of these vectors. Now, what if you want to solve BDD? I give you a target point with a promise that is not an arbitrary point in space if it's close to the lattice. But you don't want to find something within distance lambda n. You want to find a point in the lattice which is really closest to T. There are two things you can do. One is to say, I don't know how to do that. Or just take lambda n, that's the best I can do, that's the solution. Or you can bring out the dual lattice and say, okay, instead of finding n linearly independent vectors in the lattice, let's find n linearly independent vectors in the dual lattice, in this set of seemingly useless red lattice points that are not even in the right place if you look at them. And so we know that these vectors are short, they are in the dual lattice, so they define a partition of the lattice points into layers. For example, this Vi defines this partition, and you can take, just by rounding, by taking the dot product between T and Vi, you can find which of these layers is closest to the target. Okay. So so this is going to be just a line in 2 dimension. In n dimension, this is going to be an n-1 dimensional hyperplane, and you find the hyperplane closest to the target in this direction. And you do this for all the dual vectors, all the short dual vectors that you found by solving SIVP in the dual lattice. And each one of them will give you a n-1 dimensional hyperplane. And if you intersect all of them, since they are linearly independent, SIVP gives you a set of linearly independent vectors. If you take the intersection of all these hyperplanes, you will get exactly 1 point. They will intersect in a single point, and you will call this the solution to your problem. So how good is this? Now, you can show that if the distance of the target to the lattice is at most lambda 1 over 2n. So if you are a little bit closer than the unique decoding radius. So it's like a slightly stronger form of bounded distance decoding with a factor n approximation. Now, from the transference theorem, you know that lambda 1 is at most, lambda 1 over n is at most 1 over lambda n dual. And these VIs are a solution to the SIVP problem. So we know that they are smaller than lambda n, but since they are in the denominator, this is an upper bound. So you get that if T is within this distance from the lattice, then you get this upper bound. So conversely, if I give a point within this upper bound, then you will find the correct solution to the problem. So this shows how to use the lattice. So if you want to solve BDD instead of ADD, you need to move to the lattice, do something in the dual lattice, and use it using this layer trick. Now there is one last use of the dual lattice, which provides a useful perspective to look at some of the lattice problems, which is the following. So if you take the distance function, the distance of a point from the lattice, so, yes, 10 minutes, yes. It's a periodic function. It's a function that is periodic modulo the lattice. And so this suggests that perhaps you want to study this problem by working modulo the lattice. You take the Euclidean space, modulo the lattice, everything repeats. So each point, which is here in a different color, I put it with many different copies. You want to consider them to be all the same. Now, Rn is an additive group, the lattice is a subgroup, so you can take the quotient between these two groups, just using standard quotient between abelian groups. And so the elements of these quotients are lattice cosets. They are shifted copies of the lattice. And any fundamental region of the lattice provides a set of standard representatives of the lattice of the cosets. And notice each of these regions has exactly one, if you take the half-open region, so the boundary points are not repeated twice, you will get exactly 1 point for every color. And if you change your basis, you will get a different set of standard representatives, but you will still get only one for coset. And there is a different way to represent these cosets, which is by taking the scalar product between your target and a basis for the dual lattice. So when you take scalar products between dual vectors and a target, you always get an integer. Now you don't care about which lattice point is closest to the target. You're trying to forget that, to work modulo the lattice. So you can take these scalar products and reduce the result modulo 1. Take only the fractional part of the product. Notice this is not an integer because t is not a lattice point. And this information captures exactly the value of the target modulo the lattice and is useful in the formulation of some lattice problems. An alternative way is to define the closest lattice closest vector problem. Instead of the problem of finding a vector closest to a target, you can consider a shifted copy of the lattice. Notice if you move both the lattice point and the target by the same amount, the distance stays the same. So you can consider a shifted copy of the lattice and then ask, find a point in this shifted lattice which is closest to the origin. So these are equivalent problems and can be formulated using the dual lattice. Okay, so to conclude in these last 5 minutes, let me mention the random lattices used in cryptography. We'll talk much more about this tomorrow when making a connection between average case and worst case complexity. So this is just the definition. So in cryptography, often you work with lattices which are periodic modulo Q. So you can think of them as integer lattices. You only want to use integer points so that are easier to represent on a computer. And you can consider lattices which are periodic modulo Q. They contain z, qz to the d as a sublattice, so that the coordinates can be represented using fixed precision, bounded precision integers. And so these are in cryptography you can pick the lattice, or in coding theory too, you can, it's your choice, it's not given by the problem, you're building a lattice to have a good error correcting code or have a good cryptographic function, and these are natural choices. And let's look at some examples. The standard way to define these lattices is the following. There are two different ways. One is to take a matrix modulo Q and consider essentially the image of this matrix. And for technical reasons, this is often written using the transpose matrix. So you take the lattice generated by the rows of A modulo Q. So this is the lattice spanned by A. So you can also consider the kernel of A modulo Q. You can take the set of solutions to the system of equations AX equals 0 modulo Q. And now this is not a basis. But it's easy to see that it's still a lattice. It's a discrete set of points. It is closed under addition, so you have all the lattice structure. And now these two different ways to define QRE lattices are equivalent, and in fact they are general ways to do it. So these three conditions are equivalent. A lattice lambda is QRE. It is a subset of ZD that contains Q times ZD. So it repeats periodically when you add the multiples of Q. It can be represented as the image of some matrix A modulo Q, or it can be represented as the kernel of some other matrix modulo Q. Notice for a fixed matrix A, these are different lattices. One is the image, the other one is the kernel, but they are equivalent. In other words, given an A, you can find an A prime such that the image of A is equal to the kernel of A prime, and similarly, given A prime, you can compute a corresponding A. Now, what is the relation? But if you fix the same A, you get different lattices. What is the relation between these two lattices? They are exactly the dual of each other up to scaling. So the dual of the image of the lattice generated by A is the scale version by factor Q of the kernel of A. You can see this because when you take something modulo Q and then you divide it by Q, you get something which is modulo 1. So you are saying that integers go away, and that was the definition of the dual lattice. Similarly, if you take the dual of the kernel modulo Q of a matrix, that's the scaled lattice generated by A modulo Q. So last 5 minutes, bear with me. How does this relate to cryptography? Just to anticipate what you will see tomorrow in much more detail. So in cryptography, you don't need to use lattices in some sense. You don't even need to mention them. I mean, you have to mention them because otherwise you cannot title your paper Lattice Cryptography, and these days it's considered cool if you use lattices. Yeah. It was not so 20 years ago. Yeah, it was almost the opposite. So you can define them just in terms of matrices. So Untitled function, this was the very first cryptographic function, was defined as take a matrix A that is a key to a function. Think of it as the definition of the function, and the function fa of x is just computing ax modulo q. And so this is a function, and Untitled was using a set of parameters for which this function is surjective. It compresses the input, and it could prove something very interesting. If lattice problems are hard, then this function is one way. If lattice problems are hard in the worst case. But let's disregard this Untitled result. Let's try to relate this in a straightforward way to a random average case lattice problem. So where is the lattice hidden in this definition? It is precisely the kernel of A. If I ask you to find, so this is the function, and this function is restricted to vectors x, which are short. So notice here in this function, the function was restricted to take only binary vectors as input. If you take arbitrary vectors as input, the function is not one way. You can invert it just by solving a linear system of equations. So this is a function that takes small vectors to vectors modulo q, and in different dimension. And the kernel of A, we know is a lattice, is the QRE lattice defined by A. And finding a collision in this function, finding 2 points that map to the same output, is exactly the same as finding a short non-zero vector in this kernel, just by linearity. It's finding 2 vectors which map to the same value, so that if you subtract one from the other by linearity, their difference is non-zero because x and y are different, and they map to the 0 value. So you can also think of this as the syndrome decoding or dual CVP formulation, where the output of this function is exactly taking the product between x and vectors in the dual basis of this lattice, and taking the fractional component of them. Since everything is scaled by factor q, here we are taking the result modulo q, but it is the definition of CVP that I gave before. And so this is our problem. And notice if, so Untitled could define and analyze this function when it is compressing the input. In particular, the input x was short in the sense that it was a binary vector with 0, 1 components, but still it was a vector much longer than the expected shortest vector in this lattice. In fact, it was bigger than lambda n, it was bigger than the covariant radius. And so this essentially shows that the short integer solution problem, which is the problem, the name of this Untitled inversion, function inversion problem, is a form of absolute distance decoding problem, but on randomly chosen lattices. The lattices that are defined by a uniformly random matrix A. Now, the same can also be said for Regev learning with error problem that you'll see tomorrow. The problem is defined similarly, but using a different formulation. So here we consider products of the form AS plus E. Now, this may seem a different problem from SIS, but in some sense the relation between these two formulations is just duality. One is using the syndrome decoding coset formulation of CVP, the other one is using the generating matrix. The real difference between the two functions is that in the learning with error problem, usually the input, this error E, is much shorter than in Lattice function, to the point that the resulting function is injective. And that's what made it harder to prove that the function is still hard to invert. But the payoff is that it produced many more applications. And again, you can think of this time in a more direct way as a lattice problem for random lattices, where A is the generating matrix of your lattice modulo Q. You are given AS, which is a random lattice point perturbed by some error E. Error E, which is guaranteed to be within the minimum distance, the unique decoding radius of the lattice. And when you are within this radius, then the solution is unique. And in this way, you can think of the learning with error problem as an average case instance of the bounded distance decoding problem. So learning with error and SIS are the average case counterparts of bounded distance decoding and absolute distance decoding problems. Okay, so there is much more about the mathematics of lattices. The title of this talk was a little bit way too broad. But I will not talk about them, but just to mention important topics which you will find in the study of lattices, both cryptography and other applications, are Gaussian measures and harmonic analysis. This is one of the most powerful techniques used in the analysis of lattice problems. And lattices from algebraic number theory, which is a traditional topic in mathematics and number theory, but it also turns out to be key to the design of efficient applications, and they are used, for example, in many of the NIST lattice crypto standardization proposals. You can also consider lattice problems in norms other than the Euclidean one, which is a nice connection with convex geometry. Instead of having balls and Euclidean distance, you have arbitrary convex bodies. And sphere packings is another classic area with connections with the coding theory. And worst case to average case connection, that's something that we'll talk about tomorrow. And this concludes my talk.
Do you have any questions for Daniele? We'll take a few questions.
There was a point where you said that CVP and SVP were I can't remember your words, not interesting problems, or what was, I can't remember, maybe they weren't not interesting, but they were not useful.
Okay, for cryptography, let me qualify it. For cryptography, in the following technical sense, if you assume that CVP or SVP are hard in the worst case, and then I ask you, can you provably build a cryptographic function, a one-way function from it? We don't know how to do it. We know how to build functions that we don't know how to break, but we don't know how to connect, we don't know how to build the functions with the property that if you can invert the function, then you can solve CVP and SVP. So if you can break the cryptographic functions, the best that we know how to do is to solve SIVP, which is a somehow easier problem. So CVP and SVP would be a weaker assumption, would be better to build cryptographic functions out of CVP and SVP, both because they are technically harder problems in the sense that we know how to reduce other problems to CVP, not the other way around. And traditionally, they also received more attention, but yeah, so we don't quite know how to do that. If you take gap SVP, just the problem of estimating the length of lambda 1 without finding the shortest vector, then everything changes. Then yes, we know how to do that. Okay, so one way to put it is the following. We can build the cryptographic functions with the property that if you crack the cryptographic function, then you can estimate the value of lambda 1 in any lattice, but without finding the shortest vector. We still don't know how to find the shortest vector in the lattice. We can only estimate the length using an hypothetical attack to the cryptography. Does that answer the question?
It helps, certainly, yes.
Okay, I'm happy to talk more about it, yeah, offline.
And this is open. We don't know any barriers of any sort against basing cryptography on SVP, right? Search SVP. It's just we don't know.
No, there's no Yeah, so it's something that's quite possible. In fact, in principle, it may be possible to prove it based on Minkowski's problem, the problem of finding. So in case of Minkowski, computing the bound is trivial. We know how to compute it. It's just the determinant of the lattice. But if I ask you, you want to find a vector within Minkowski's bound. We don't know how to do it efficiently, but we don't know how to build the cryptographic functions out of the conjecture hardness of this problem.
And sort of on the average case, these problems all turn out to be, for example, solving the cis problem, inverting Lattice function. It's solving in a sense, it's solving SIVP in the sense it produces one vector that is smaller than
On the average case, SVP, SIVP, I mean, they are the same because they are random lattices, so all the minimas are going to be concentrated around Minkowski's bound. So all these problems collapse to one, and in that sense, so we know how to build the cryptographic functions from the conjecture that SVP is hard on the average. So that we can do. But if I say that, no, I only want to assume that it's hard in the worst case, then we need to start from SIVP. We don't know how to do cryptography starting from SVP. And it's a technically, intuitively, yes, it should be possible, but we don't know how to do it. And the problem has been open for the last 20 years. So there seems to be some technical difficulty. I'm not saying that it cannot be done. In fact, intuitively, I would say it should be possible to do it, but it's an open problem. Yep. Yeah.
Probably just an opinion. What do you think a worst case lattice look like? It's the average case are actually the hardest, or
okay. So So that's what the worst case lattice is. So make a list of lattices. Not on your list. Okay. They look by diagonalization, which is what I was trying to impersonate before. So it's somehow elusive. If you pick a lattice, then the problem becomes easy by definition in the sense that the solution is fixed. There is nothing to compute. You can just look up the corresponding answer on a table. So hardness is not a property of a single lattice. You still need to consider.
in terms of the metric of the lambda 1 to the lambda n.
Oh, in terms of the geometric properties. So I think that worst case hard lattices can still have lambda 1 equal to lambda n. So these extreme lattices, I expect them to be hard in the worst case. But on the technical side, those are the lattices for which some of these problems become easier or equivalent in the sense that there is no difference between finding vectors within. So SIVP and SVP become the same in the case of extreme lattices. So there are these technical difficulties, but yeah, it's not an easy class of lattices. Are the lattices that are in a sense farthest away from being orthogonal. And orthogonal lattices have, even if lambda 1 is equal to lambda n, you have a square root of n gap between the lambda 1 and the covariant radius. A random lattice is a lattice where all these numbers are expected to be close to Minkowski's bound, and that's where geometric rounding techniques start to fail very badly. And yeah, I think that's hard.
Intuition is, or like everything we know algorithmically suggests that the hard case is the average case actually, right? Like as far as we know, random lattices are basically the hard instance, but like proving that formally doesn't seem plausible, right?
Yeah. So in fact, you can think of a scale. So if you take the standard form of, say, average case, worst case connection for problems like discrete log is, you can randomize your basis. If you can solve a random instance of the problem, you can solve every instance of the same problem. Now, in the case of lattices, we are not taking arbitrary problems in the worst case. We are taking this random class of lattices. So it follows as a corollary that if you can solve these problems on the average, on this class of random lattices, then you can solve them in the worst case over the same class of QRE lattices. But you can do even more than that. You can even solve problems which are not QRE. So there is this mismatch between the two classes. There is also a mismatch between the approximation factor. When you go from worst case to average case in lattices, you are losing typically a polynomial factor in approximation, polynomial in the lattice dimension. So there's a little bit of a gap. But yeah, so if you want, you can take the worst case lattices, restrict them to random. Of course, the problem of gap SVP on random QRA lattices is trivial in the average case from concentration. For the search problems, should be hard in the worst case.
So, maybe I'll push back a little bit, right? So aren't there algorithms that work sort of heuristically, but you can't prove any worst case bound. So in other words, heuristically, as in under the Gaussian heuristic or whatever. So random lattices actually seem to have better algorithms than worst case lattices. Isn't that?
Yeah, but it's not clear if that's just because that's what we've studied.
That's our inability, or
yeah. We don't know an example of like a lattice a class of lattices that seems to be harder than random lattices for any like. Yeah. Although I only know like 3 examples of lattices, period. So random, integer, and direct sum of the two.
So another way to illustrate this is start from algorithms. So pick any algorithm, and the best that we know how to prove is that the algorithm finds approximate solutions to SVP within a factor which is exponential in the dimension of the lattice. It's very large. Then you may ask, can you show that the bound is tight? Can you find a lattice where your algorithm behaves in the worst possible manner? It really gives that. And you can do it for LLL. You can build examples that achieves the worst case approximation factor, but only if you pick that basis and you say, that's the input. If you do something as simple as randomize the order of the basis vectors, then the algorithm will start behaving better, improve the solution, and we do not know how to build a lattice basis where the algorithm achieves the worst case approximation factor, so it behaves as badly as we can prove for any permutation of the input basis vectors. So you could define in principle a random class of lattices, which is this specific lattice, but by randomizing the order, and that seems to make it easy in some sense, but it seems really a technicality. Yeah, I think it only says something about how poorly we still understand the geometry of lattices and their interplay with algorithms.
Okay, so further questions can be directed to Daniele after the.
Yeah, I'll be here for the whole week and beginning of next week as well.
So we have a lunch break and we'll reconvene. I think at 1:30.